Good, yeah. All right, so thanks, Gabriele. Thanks, everybody, to have me here. Let's see where I should look. Yeah, so I think the original title has to do with stochastic gradients and projections. I shortened the projection part and I added a lot of math because I thought at the end of the day that's what everybody wanted. Particularly my talk compared to one, Chris is going to have 2 pictures, so I'm going to show you right away, and then the rest is going to be symbols, so I'm sure you're psyched. So I'm going to present kind of a string of work that we start doing probably 2015, and the last one came out now with several co-authors. Here's the list: Silvia Villa, who was in Milano, now she's back to Genova, Yunong Hing, who's now in China, Gergely Noy, who's in Barcelona, and Nicole Muck, who's Muck, I guess, where she's now in Stuttgart. The broad constant is essentially the observation that there are tons of results of SGD, which is probably the most common algorithm in machine learning. There is a bit of disconnect between the kind of results that you find in theory and the kind of algorithm you use in practice. So what I'm going to try to use, and I'm going to pimp up a bit the algorithm while considering a simple setting when I can try to characterize the effect of my algorithmic choices. So that's what I'm trying to do. So let me a bit of warm up. Perhaps the rough context, this is picture 1 and 2, is we're going to have a lot of data, we're going to have a lot of dimensions in our data, and in the end, each computation is going to cost a lot, okay? So not only you want to have good accuracy in terms of predictions, but you also need to have something which is efficient. And one end up going back to very simple algorithms that essentially can be where you can afford many iterations, but each iteration costs relatively little. And here, I guess, stochastic gradient is the algorithm. This is the place where it lives in Italy. It's actually, there's a bunch of things going on here because I'm going to look at different kind of extension of SGD. For example, when you cycle over data, and we're going to discuss early stopping. So this is fantastic. This is the last time you're going to see a picture in this talk. All right, so what is the basic setting I have in mind is stochastic optimization, okay? So I'm going to make this even simpler, but for now just think of a minimization problem where the specialty is that the objective function is expectation. The parameter where you want to optimize over, this clearly doesn't work too well, is W, okay? And Z is a random variable. The catch is that the distribution of Z is unknown. So all you receive are sampled according to Z, samples of D, and all the samples are identical. They're all coming from Z, and they're all independent. All right, so in this setting, the basic algorithm, the basic instance of SGD is essentially saying, at each iteration, take a step in the direction of a gradient, which is not the gradient of the true objective, because you don't have access to it, but just a piece of what you call stochastic gradient, which is this thing that you see there. It's basically the derivative, the gradient of the integrand at one of the points you have at disposal. And this is called stochastic gradient because if you take the expectation of this gradient, you obtain exactly the expectation of the true gradient, okay? This gives right to use the term stochastic gradient. It actually doesn't give the right to use the word descent because this is not a descent method, okay? SGD is the kind of running name, and I'm going to use it throughout, but as soon as, for example, you ask about the convergence of this method, you typically see that something is needed to counteract the lack of a descent of the iteration. So the objective function doesn't decrease at each step. Here, let me just show you a basic result. This is one of 5 billions you can find of this. These methods go back to the 50s, and from then there is a ton of results. And this is basically a result that says if you consider the average of the iterates rather than the last iterate, and now you go and compare this to the best possible solution of the ideal problem, the one where we have infinitely samples, okay? The true objective, if you choose an appropriate step size, say 1 over the square root of n, then in function values, you're going to receive an error which is roughly 1 over the square root of n, okay? This is one basic result. I imagine many of you are familiar with it. To the sake of my discussion here, the point that I want to make is just here, the idea is that you receive one gradient, and then you take a step, and when you run out of gradients, you stop, and there's nothing else. And if you look at the proof of this is crucial because there is this conditional independence of the iterates one to the other, which is really a building block of the proofs, okay? Why do I emphasize this? Because basically what I want to look now are variations of this scheme that, that's kind of my argument here, that are the ones that are used in practice more often, okay? For example, I don't know anybody actually does one pass over the data. And they're like, yeah, it's 4 or 5, but maybe it's not 4 or 5, maybe 15. What's going on? Why you take multiple steps? What is the effect of multiple steps? the step size, again, sometimes you do take 1 over square root of n. I personally see more often some fiddling, you know. You look at data and you try to do some data adaptive procedure to try to see if there is something better or not. Cross-validation is the classical way you do this kind of stuff in machine learning, for example. And you can keep on going. There are things like mini batching. Rather than take one gradient estimate every iteration, you take a bunch of gradient, a mini batch of gradient estimates, and then maybe rather than just doing uniform averaging, either you don't do averaging at all, or you do some other kind of averaging, for example, some form of weighted or tail averaging. What is the role of all of this? Where does it all fit in this story? What is the effect? How do I choose this parameter? Now, instead of one parameter, the step size, I have 5. How do I choose them? Can theory somewhat give me at least some qualitative indication of how these parameters interact with each other? And this is the goal of this talk. A word that is going to appear often is this idea of implicit regularization, as opposed to something more explicit, I guess. Okay. You will see that in some sense, the claim here is that all these parameters controls the convergence as well as the stability of underlying flow of solutions, and there's going to be some nice interplay that you can view as a form of regularization going on. All right, so as promised, I'm going to look at all these variations of the algorithm, but I'm going to put myself in a very simple setting, just linear least squares. Okay? So my objective function now is not just a convex function, it's actually a linear squares function. And I'm going to consider a model where the random variable is a pair of input and output distributed in some way. And my model is linear. Okay? So particularly simple. And you'll see, and I'm going to use this throughout like a lot. Everything I'm going to say uses this really a lot. There is the hidden linearity in the square laws, and I use it all over the place. So can I generalize this? Not really, I'm working on it. But everything I said right now, it's more of a proof of concept that I can see the effect of certain things in a setting where I have a lot of control of things. Of course, it'll be nice to generalize this to other loss function, other norms, other function model. That's, as you see, that's in the plans. Perhaps the one observation that makes this setting not completely 1950s, more like 1965, is the fact that we consider input space to be infinite dimensional. This makes the problem a little more interesting, and perhaps one way to see why this is a bit more interesting is take the gradient and consider the optimality condition. It's easy to see that the optimality condition of this problem can be written in terms of a linear equation, which is the second moment equation of the input and the cross covariance of the input and the output. And the moment the input space is infinite dimensional, this linear equation is ill-posed in the sense that the operator is really not invertible. Okay? The inverse of this sigma, you might call it covariance operator, is not invertible. So the problem is really ill-posed. There is a really instability going on. Even if it's finite dimensional, you can have the case where the matrix is a very bad condition number. And so you really have to do something to stabilize the problem. You cannot just optimize in some approximate way. You need to worry about the fact that the moment you have sampling and noise, you can receive some instability. Okay? Because the operator is also not unique, what we're going to shoot for is the minimal norm solution among all the solution of the problem. Okay? And in particular, we're going to consider a minimal norm where this is the L2 norm. There is the L2 norm. This is the norm of the ambient space. Okay? You can also consider other choices of norms. We're going to consider this because we're going to see that this norm is hidden in the stochastic gradient descent. It's hidden somewhere in the way it computes gradient, and that's why it will actually go there and not just in any place. All right, so this is my setting. Let's see the algorithm. The algorithm is the one I showed you before plus one letter. Okay? The letter is small, it's written in red, so that you can try to see if you catch it. The only point is that the way you access the point is not just once, but there is a IT, which is the way in which you access this point. Okay? You can see the point once. Well, you can see the point once, but you can also see them multiple times. And the way you see them is, well, we can decide, and I'm going to show you 2 out of the 3 ways you can do it. One way is you pick an order of the points, you visit them, and then you start from scratch. And you always visit them in the same way, and this is what I might call the cyclic order. Okay? Or you can pick point uniformly random and put them back, so that you can actually see a point more than once. Okay? So with replacement. So you can now see a point more than once. When you go over the data once, really doesn't mean that you pass over the data once. You see on average you see them once, but you can see a point twice and a point never. Okay? But then you repeat and you go multiple times. I'm going to talk about both this. The third way of doing things is where you permute the order each time you pass over them. okay? And I'm actually going to discuss this, but this is kind of the third common way of doing things. As you see here, the number of iterations doesn't have to go up to the number of gradients you have, the number of points you have. You can actually take multiple steps, and the step size as well is going to be an algorithmic choice you have to worry about. Notice that there are no explicit penalties or constraints. So if this method will be able to control the posedness of the problem, it has to come from one of these parameters, or all of them, or in some combination, okay? All right, so let me go back. Oh, well, let me go back to the fact that you can ask, okay, nobody studied this before? No, actually, this algorithm was studied a lot, but for a different question. The question of minimizing not the true risk, but the sum of empirical error. And there are a lot of results. And basically what you see is that as the number of iteration goes to infinity, then, sorry, there should be a t here. This n should be a t. As the number of iteration goes to infinity, the empirical objective, the training error, if you wish, in a machine learning scenario, is going to converge, okay? Long story short, maybe this is important as a step of the proof. It will not be, but this is not the problem I care about. I really want to know what is not the training error, but the expected error, okay, the test error of my method. And so this in itself doesn't give me much. All right, so let me show you the first result. The first result, let me just put it there so you can start to digest it, is the first result that we have in this set. And we consider the stochastic gradient with the cyclic order of the data, so no stochasticity in the way I access the data. The only thing which is random is the data themselves. And this turned out to be probably not the best way to start because it was complicated, much more complicated than the rest we did, okay? We only managed to look at the convergence of the iterates, not of the error, not of the function value. And we needed some assumption to actually get rates, okay? And the assumption is a standard assumption in inverse problems or nonparametric statistics. You can view it in a bunch of different ways. You can view it from a statistical point of view as a kind of sparsity assumption. You can view it as a kind of smoothness, Fourier decay assumption. And from a statistical point of view, Guillaume taught me that you can also view it as an infinite dimensional generalization of some form of local strong convexity, according to the Lorenzo condition of your objective function. Okay? What he basically says is that if you look at the solution on the eigenbasis of this operator sigma, it has some kind of decay governed by alpha. The bigger is alpha, the simpler is your solution. So not only the solution has to satisfy the normal equation, but in some sense it lives in a smaller subspace of the space generated by the eigenfunction of the operator. Is the source condition. I raise your hand and say it, no? Okay. All right, that's it? Yeah, so this condition, nobody really likes it. But it turns out that that's really what you need. In infinite dimension, you cannot get rates unless you make some kind of assumption. This is the assumption you want to make in this setting. Once you make this assumption, you can now prove a bound that compares the multipass cyclic stochastic gradient to the best possible solution of the expected error. And you can do this for any, you're going to fix the step size to be 1 over n, kind of small. Francis Bach would hate this, but this is what we could get 5 years ago. And then we have this decomposition for any t, where you see the appearance of two terms, a convergence term, and then a stability terms with respect to the number of points. If you optimize and get the best possible stopping time out of this equation, you can get the rate and you get the stopping time, okay? Well, before I comment on this result, let me just give you an idea of the proof. The proof, as I said, has to be different because here the data are seen multiple times. And so they're all wound up and forget about condition independence about your data. So the idea here is that don't do that. The expected gradient, so the idea here is that the thing you want to look at is the gradient descent of the population, okay? This thing here. And that, of course, goes to the right place. If you look at the iteration, when you could hallucinate and take the true gradient, it goes in the right place. The idea here is that when you look at your empirical gradient, based on these multiple passes, this might go at the beginning hand in hand with this ideal population, and then at some point, it turns, not like a sharp angle, maybe it goes at the different things, but then it goes and minimizes the empirical error. And the idea of the proof is that we want to somewhat take into account this behavior and try to see where we can stop the algorithm to be, as close as possible to W dagger. So this is really the structure of the proof. The first part, this one here, is the convergence. The second part, this one here, is the stability. So when you look at these bounds, the second term is the convergence, the first term is the stability. That's it. There's nothing else going on here. But because I really want to impose you something, in this case, convergence, because it's all linear, can be studied not with tools from convex analysis, but just from linear algebra, or if you wish, spectral theory, okay? And if you just compare the true gradient with the exact solution, you can just simple manipulation, and it turns out that this equation here, I wrote all this stuff because I wanted to take a look for the first time at this equation here, and of course I forgot that eta is identity minus eta sigma to the t. This is what governs the convergence of this method if you have infinite data. Okay? And so you see that the familiar exponential, linear rate if the matrix is invertible, and a polynomial rate if instead it's not invertible. For the stability, and I just want to show you this one equation here to give you the feeling why this was painful. Because if you look at the iteration, it's kind of a batch gradient. It's a gradient descent on the data plus an error term, and the error term is ugly. Luckily, hidden in there, you can view it as a kind of, you can view multi-pass stochastic gradient as a noisy batch gradient descent, empirical gradient descent, where the noise is very structured. And it turns out that there is a Martingale structure hidden in that noise, and that's what allowed to actually control the error. Okay? But this is kind of what made this, we tried to improve these results, but the structure of this noise made it complicated, at least to us. All right. The good news is that we still can manage to get a result for the first time, at least to my knowledge, for multi-pass stochastic gradient in terms of true risk. And what we have is that no averaging, deterministic stochastic gradient, what I mean that it's really not stochastic, the data are stochastic, but I'm not having any stochastic access to the data, goes to the right place in terms of iterates. We get the rate, and the rate is optimal. There is a matching lower bound. And instead of doing iterate, instead of just doing optimization, you first do this and you just study the property of this empirical variational solution, you get the same rate, exactly the same rate. So this suggests that here is the number of passes that enforces regularization. This method does converge to the minimal norm solution, so it looks at the space with a bias. It likes minimal norm functions. Not only that, the number of iterations parameterize the path of possible solution and controls the regularization level. Okay? Now, in practice, of course, you don't have this magic alpha that I invented to get rates. You don't know it, okay? But you can get the same results if you do, for example, some classical things from statistics like a cross-validation, hold-out cross-validation, or Letzky principle, okay? So what you're going to do in practice, you're going to do some data-driven procedure to choose the stopping time. Say you monitor the error on a side of a data set aside, and you see when either you see a plateau or the curve going up. Okay? And this justifies this, not just as a hack, because basically I can prove that the same stopping rule, that this kind of adaptive stopping rule gives you the exact same bounds. Okay? So we tried to improve these results quite a bit, okay? But ended up being very technical. So what we did is that we actually turned to the stochastic version of this. So rather than picking an order and going with it, each time we take a step, we pick a point at random, and then we put it back. Okay? So this is really the most classical form of stochastic gradient, and it turned out that this was a bit easier to study. So in this case, we get a similar bound, okay? I'm going to start to show you a bunch of results, and the details of the results are not so important. I just want to point out several points. So here the point is that, notice that we are not looking at iterates anymore, but function values. So this is the true error. We expect better rates. And also notice that now the bound has 3 terms rather than 2. As I show you the bit of the proof, it's going to be clear why. And notice that what really matters is not just the number of iteration, but the product of the number of iteration and the step size. So in some sense, the amount of road you're going to be able to make. Okay? How long is the step and how many steps you take. Basically, that plays the role of the regularization parameter. And now, once you see this, you can now play with a different way. You can choose this, optimizing that bound above to get good statistical bound. Okay? And what you see, for example, is that you can if you take a small step size, you have to do more passes. If you take a bigger step size, of course, you have to do fewer passes, but you always get the same rate. Okay? Out of these results, of course, you can say, okay, much out of for nothing, because you just see that the previous result was the best you could do, okay? And indeed, in this worst case scenario, where the only thing you assume is that the minimizer does exist, you see that you can study multiple passes, but there is no obvious reason why you should do it, okay? Of course, you can now ask, oh, can I get more refined? Okay, so notice that you still get convergence, okay? This bound is, again, good, and is as good as the bound you get for empirical risk. And you can also prove the same results for iterates, okay? So you see that the method does converge to the minimal norm solution and parameterize regularization by now the product of the step size and the number of iterations. Now, you can try to get faster rates, and here we were able to further improve. So I already show you what this first assumption over there, that kind of sparsity assumption. This tells you that the solution lives in a subspace. Now I can make a further assumption that tells you how big is the biggest space the solution can live in, okay? Which is an eigenvalue decay on the covariance operator. These two conditions are independent with each other, and they're going to both contribute the rates. In the first case, big alpha is what I like, because it means that the solution lives in a very small subspace. In the second case, I like, oh, there is a mistake there. It should be 1 over gamma. I like small gamma, which means that the solution lives in a space which is close to be, the space itself is close to be finite dimensional, okay? Should be 1 over gamma in the convolution. Everything reduced to the worst case if I take alpha equal to 0 and gamma equal to 1, okay? Now, the bound becomes ugly, as expected, because everything now depends on these parameters. The reason why I'm showing the one above is just that you see that now everything depends on these two parameters. As you can expect, now you can again optimize in different ways, and you get this final bound here. So this one is a bit more humane, and this is start to look like bounds that you might have seen in statistics. Indeed, is the optimal non-parametric bounds from statistics, okay? Depending on this kind of condition. So this bound is good, is up to constant, is not improvable. Now you can play the same game you did before. You can say, okay, let me just dump everything I don't know on the step size, or let me optimize for the step size, or let me optimize for the number of passes. And here is a little bit more interesting, because you have to choose something depending on this unknown smoothness. It's either the step size or the number of steps, but one of them, or maybe even both of them, have to depend on them. So of course, if you're God, you can say, well, I'm going to choose the number of passes to be n, and then I'm going to choose the step size like in this second choice. But unfortunately, you're not God. So now you have to do cross-validation. Now you have to somewhat do an adaptive way to choose parameters in such a way that you approximately can hope to adapt to this condition. And I think this somewhat start to be closer to what seems to be happening in practice. What you might do is that you fiddle around a bit with the step size, you fiddle around a bit of the number of passes, and then you try to find a data-driven criterion to try to find a good pair of choices. Okay? If you do a super simple simulation where you just see if this happens, I apologize because this was a picture I didn't announce. You see that indeed the stability of the method, you can fix the number of steps, and then the step size is going to do this kind of stability control, or the other way around. Okay? And this is a simple scenario where we put a lot of noise, so you have a lot of overfitting. You might have situations where you just have plateaus rather than a U-shaped curve. All right, so notice that all this is because I go beyond worst case and I start to see what happens under more benign condition. Because after all, I invented all these conditions. So you don't know when you see data what's really going to happen. And just assuming that the minimizer exists without further assumption doesn't really reflect what you might have in practice. Okay? The idea that the solution is simple or the space is simple depends on the data, and you don't have access to the true distribution. All right, so I think I can skip this because this is basically the content of this. The proof here, I just mentioned quickly, all the rest is going to be the same. The proof here follows a slightly different path. Here we have two sources of stochasticity, the data random, and we pick the point at random, okay? So we now have to somewhat fiddle around with both these things. So what happens here is that we actually split there in 3 terms. It's still true that gradient descent is the guiding force, but we've also introduced the gradient descent, the full gradient descent on the data. So the guy on the left is the batch gradient on the population, where we have infinite data. The one on the right is the gradient descent when you have a finite number of points, but at every step you look at all the gradients. Then it's split there in 3 terms. The convergence of the population gradient with infinite data, the convergence of the discrepancy between the full gradient on finitely many points, an infinite point, and this is just depending on the data, okay? On the stochasticity of the data. There is no stochasticity in the gradient. The last step is how far is stochastic gradient to batch gradient. Here the data are fixed, and the only thing which is random is the way I access them, okay? And so this is somewhat allowed to recycle the conditional independence, because here everything is conditional independence once you condition over the data. The way you access the data every time is independent. So you can split the error term in 3 terms, and these are the 3 error terms that appear in the bound. All right, so to the best of my knowledge, again, this is again one of the few results that allows to go from one pass to multiple passes and understand the role of these things when your goal is expectation rather than just optimization of empirical objectives. All right, so this is really the main part. I want to have like 15 minutes, 10 minutes, like 5 minutes. What I wanted to show you is this effect. Yeah, multiple passes and step size, and start to unveil how they interact when you take more pass than one, and when you start to make more benign assumptions on the data. What I want to do is to take another couple of steps. One, introduce mini batching, and if I have time, I also would like to show the most recent result, which is what happens when you do averaging. So mini batching is this story here. The notation is a little annoying. It's very easy to say in words. At every step, you pick at random B points out of the one you have. You compute the gradients for each of them, and then you take a step. Okay, that's it. Rather than 1 point or all of them, you go in between. You take B. This is what you do when you have a real computer, because you basically look at how much memory you have, you choose this mini batch size, and you try to avoid looking at the hard disk too many times and use your memory as well as possible. Now, notice that I'm going to keep here again, the point I'm just looking at uniformly at random. B is a new parameter I have to choose in practice. And when I talk about number of passes, it's going to be this thing there. The number of iterations times how many points I use per iteration divided by the total number of points. Okay? That's what I call a pass over the data, because it's roughly how many steps I need to take before I, on average, look on all the data set. All right. So here's the bound, and again, the bound I put there. At this point, you might have some, inception of the bounds you saw before. So you can focus. The main difference is that, well, the only difference is that up to higher order terms, the only difference is that in the last term, you see there is a B dividing the step size. So the mini batch now appears at the numerator below the step size. So you can expect that if you're shooting for 1 over square root of n of the total bound, if you now can allow the batch size to be larger than 1, then you can allow a larger step size. Okay? And that's basically what happens. And something kind of interesting happened, or at least something that for me was well, it's kind of obvious now, but I guess I did not expect it. If you take b equal to 1, you're back to 1 pass of the data, okay? And you end up having the same result I showed you before. If you start to increase the mini batch size, you do see that you can increase the step size. And the moment you get the mini batch size to be square root of n, the step size becomes constant. It's like you were looking at all the data, like if you were doing the batch gradient. And you can do just 1 pass. If you keep on increasing the mini batch size, all these bounds are the same in terms of statistical terms. If you keep on increasing the mini batch size, you have to just do more steps. Okay? So this result suggests that there is no reason why you should do mini batch size of dimension larger than square root of n, okay, from a computational and statistical point of view. In hindsight, if you want, this says you can expect the mini batch size to reduce the variance of your gradient estimates, but your data already have some variance, which is roughly order of square root of n. And so when your variance in the gradient is the same order of the variance of the data, you're done deal. You can go above it, but it's like going below noise level. You don't want to go below noise level. So this fact that there is a critical mini batch size was kind of interesting to me. You can go the same stuff with faster rates, okay? Everything becomes more complicated. You have again a critical step size. Now the critical mini batch size is qualitatively you have exactly the same take-home message, okay? Everything is going to depend on the unknowns. And now you see that you have the 3 parameters. You have the mini batch size, the number of steps, the step size, and they all have to be chosen in some kind of data adaptive way once you don't know the parameters, okay? You can choose one, but at least one of them has to be chosen in a data adaptive way. I'm just showing this. bound here because you'll see that the moment I combine averaging and mini batch, I can get even a bit more mileage out of this whole story. Okay? But roughly speaking here, the take-home message is the same one as the slides I showed you before. All right. We now have the mini batch, the step size, the number of passes. If the one thing which is kind of I didn't discuss at all is averaging, which is actually the first thing I discussed. Okay, averaging is the which is very old, as I told you, because the method is not a descent method. It is the easy way to get rates. You actually to impose something like averaging. But more recently, to actually emphasize by it was somewhat advertised. We say it was high. Oh, I'm tired. It was shown in a series of papers that if you actually do averaging in this precise setting, you can actually do larger step sizes. Okay, this was shown in the first in the finite dimensional case where you can get a constant step size, and then in the infinite dimensional case where you can get larger step size than the one I show you in certain regime. And the first paper that made this observation was a paper by Francis and Moline, and then there was a paper by Émeric Dieulevé and Francis Bach that considered the infinite dimensional setting. Okay, these are my two reference points. So the question is, can we get this kind of results? But before discussing this, there is another observation that these very same papers also show that averaging is not only giving you something more, it also can spoil the rates. There are regimes in which, by doing averaging, you get slower rates. Okay, and I'm going to review this in a minute and show you how, if you rather than doing uniform averaging, you do some kind of tail averaging, then you can go back to the good rates. So this is the kind of averaging I want to look at, okay? Is the averaging where I not only, so WT here is going to be the same kind of mini batch, multiple passes, stochastic gradient I showed you a second ago. And then what I'm doing is that I average the last t minus s iterates, okay? If I choose s equals 0, it means that I average everything. If I choose s bigger than 0, then I have a length tail L, which is the number of iterates I consider. To understand a bit the role of this averaging, I found useful, so I'm going to share with you the calculation of what happens if you just do averaging of the true gradient. Okay? Rather than the stochastic, look at the true gradient. I show you that if you do the true gradient on infinitely many points, the convergence rate is governed by that exponential there, identity minus eta to the sigma t. What happens if you actually do, and this improves for any alpha, okay? In the infinite dimensional set, you get these rates. For any alpha, these become faster and faster and faster and faster. If alpha goes to infinity, that gets arbitrarily close to 1 over t. What happens, sorry, to be exponential. What happens if you do tail averaging of this full iteration? It basically happens that if you look, again, you can show that there is kind of a polynomial residual, like the one above, that control the convergence of everything, but the one that you obtain looks like this. So you get identity minus eta sigma to the s plus 1 divided by t. Then you get some other terms that are somewhat higher order. What does it mean? If you take s equal to 0, these exponential terms disappears, and you just get the 1 over t. If you get s, say, equal to t half, then it looks like the one above. Okay? And this is indeed what happens even when you replace the true gradient with stochastic gradient, that's what happens. If you just do gradient descent, stochastic gradient with uniform averaging, once you reach these 1 over t rates, even if your function is super simple, the rates doesn't improve anymore. Whereas here, this suggests that perhaps if you do tail averaging, then you can recover and adapt to this simplicity of the solution and get faster and faster rates. Okay? This is a super simple calculation, and that's why I'm showing you. And to me, it was kind of refreshing because I understood a bit the role of averaging. If I now just throw in your face the results where now I do tail averaging, mini batching, stochastic, step size, and all of it, okay? I kind of give you the takeaway message already. You can expect the tail averaging is going to give something to you, and what does it give you? If you want to do uniform averaging, you have to look, the rates are going to stop improving after alpha equal 1/2, okay? If you do tail averaging, you can actually go above and keep on improving. So if you do tail averaging, you can always get rates. The rates you get are again optimal. You see that you get this extra term in the last term. And what this gives you essentially is that we're going to get something better for the mini batch size. Now that we see the interplay between the mini batch size and the uniform averaging, we see that combining the two, as one might expect, gives you something. So here's the whole story of how you compare this stuff to the results we had before. If you consider one pass, so mini batch size 1, exactly one pass over the data, we recover the result by Dieulevée-Bach for uniform averaging. But we show that if you now consider tail averaging, you can actually exploit the smoothness of the solution all the way for all the regularity levels. If you look at the result that we had before with mini batching, but no averaging, now you see that averaging combined with the mini batch gives you something. The critical mini batch size, in the case of without averaging, is that expression there, where is a 1. The one where you combine averaging and mini batching has this gamma. Remember, gamma is between 0 and 1, and in the easy case is 0. Okay? So what matters here is that that thing for easy problem becomes smaller. And you like it to be small because it means that even if you do mini batch size that are relatively small, you're as good as if you were doing the full batch gradient. Okay? And the proof is kind of a combination of a recent, so it's basically combined the previous results with some recent idea developed by Francis and co-authors. All right, so this is basically everything I wanted to tell you. The whole catch here was that you can study the learning properties of variants of this SGD that are practically used, at least if you consider this kind of simplified setting, which is linear least squares in infinite dimensions. Okay? You do see that all there was no regularization explicit in any way, and it was just the mini batch. Every parameter introduced, one way or another, can be seen as controlling an interplay between stability and convergence. Stability with respect to the convergence in the data, stability with respect to the stochasticity in the data, stability with respect to stochasticity in the algorithm. To me, this is just the beginning of the story. Okay, I'm in no way claiming that this is the end of it, but it's just a proof of concept where I see that certain things can happen. Okay. And now you can start to ask questions like the one, you can ask a bunch of questions. A few we already start asking. For example, can you combine these things with the idea of random projection to make the algorithm even more efficient? There is a line of work on that I didn't have time to talk about. What about these magic properties you introduce? Alpha, gamma, what are they? I mean, what if they're wrong? Well, luckily the theory holds for a vast class of condition. Rather than polynomial condition, take logarithmic condition or exponential condition and see what happens. You can adapt the whole theory to classification, and classification can be super easy. Okay? You can have separable classes. So you can take this theory and now take a whole bunch of corollaries and try to see which is like in physics when you have a model and then you have different assumptions that drive the model. Then you have to see which one explains the data better. It's the same thing. It's like a theory that can be tried to be predictive of what happens in practice. There are a bunch of results in this direction. Much less is done if you start to ask questions of try to generalize things mathematically to other loss functions, other norms, and especially other function classes. We did some steps for other loss function, other norms. The big thing here would be to try to go beyond linear models, because essentially this is now widely considered one of the main ways to understand the practical empirical properties of deep neural networks at training. It's well known at this point that you can turn off all the things that you would thought they were doing something for regularizing, and the gradient descent herself, I don't know, is actually going somewhere good. It looks that there is an implicit bias. It looks the number of iterations under parameter do control the complexity. Here, this shows that at least in a simple setting, we understand that. Okay? The idea would be to try to prove it for nonlinear models. And I think that's really like the big one here, going, if you want, beyond the convex case to the non-convex case and try to, at least with some structure. Everything is online. The last paper just came out 2 months ago, and the shameless plug, I'll leave it there. All right. Thank you.
So questions for Lorenzo?
Yes.
Yes, Christoph.
I saw once on your slides, not in this talk, that you connected the spectral filtering with the implicit regularization. This is very nice from an inverse problems point of view because you can make the regularization actually explicit. Mm-hmm. Is there any chance in this scenario to still see specializations of that spectral filtering?
Yeah. So I mean, if you want, basically everything here shows that when you do stochastic gradient, it's a perturbation of a spectral filter. It's a spectral filter plus. an error term. The method itself is not linear anymore, so there's no hope to prove that it's a spectral filter itself, but you can prove that it's a perturbation of a spectral filter and show that the error is small and disappears as the number of iteration and the number of points grows. But that's exactly.
And there's no hope that this would give you more insight in the geometry, or let's say the.
I mean, you just open the hood even more. That's basically what's going on. Okay. So I do think that that's what that's exactly what gives you the insights here.
So thank you for the talk. So based on almost the same assumptions, you present some similar results. For example, for multiple passes, some different step size, different size of mini batch averaging or not. I wonder, can we obtain some similar results with like using shrink step size? Like the step size is 1 over the square root of t, or otherwise using some important sampling, what's the performance of these kind of algorithms?
So the first question I didn't understand. So you want to like a step that doesn't depend to the end but changes every.
Yeah, you change every.
Yeah, so I didn't say, but everything here can be. We have for the second set of results. So everything generalized to that setting. So you can take, instead of a constant step size, you can take t to the minus theta and then choose theta depending on stuff. So everything I showed does, we do have those results. For the adaptive sampling, we are thinking about it. I don't know. It would be very, I mean, I think it's one of the big questions. Can you do it in this kind of setting? This setting is simple, but it's complicated enough that it's non-trivial.
Would it make sense to use more complicated averaging strategy, or?
So what we started doing was weighted averaging, and then we just got a bit lost. And it turns out that tail averaging was the one that we could really handle and see the effect of. I think yes. In practice, you do see that averaging really have a strong regularization effect, and it would be very nice to. We consider a particular case of averaging, which is kind of a geometric series, in which case you can see that the component of the geometric series are essentially related to a Tikhonov-like regularization. So certain kind of averaging are equivalent to penalization. So we have a paper with Gergely Noe last year in Cole that essentially show that. But it would be nice to have a very general theory, and we don't have it yet.
Short espace.
Pour Guillaume. We know each other. You can tell me later.
Once you introduced lambda, regularization parameter.
Quickly, but then I show it.
Yeah. Yes, but then you overwrite this value of lambda, assuming that lambda goes 1 over t.
No, I just said, I don't put lambda, but it's like as if I put it. That's what I did. So my point was, I never put a lambda in anything I said, okay? My comment was, but if you wish, is as if I added one that went down as 1 over t.
Okay. So, but there is not any lambda.
No, it's like this. No. That's exactly the thing. If you want, the surprising fact, again, if you don't think about it, is that hidden here, there is going to the minimal norm solution. It's hidden in the way you define the gradient, essentially. So you don't need lambda. We've been working with this gentleman here about other loss function and other norms. In that case, it's not so clear if you can just do such a scheme, and maybe you do have to penalize and take a diagonal approach and let it go to 0. At least that's how we know how to do it now. But this case, there is no penalization whatsoever.
Okay, so if there's no questions, let's thank Lorenzo for his talk. Okay, so I think it's time to thank Alain for his talk and all the speakers of the conference.